When we're using the comparison test, we're comparing two series, but we're only given one to start with. The other one we have to come up with. There's basically never just one right answer. There's usually a whole bunch of different series you could compare to that would work, but there's also a lot of series you could try to compare to that wouldn't work. So here are some basic guidelines for choosing a comparison series. The first thing is the one we compare to needs to be easy to deal with. If I don't know whether the comparison series converges or diverges, then the test is useless. So we like to have series whose convergence or divergence is obvious to us. That usually means in practice a p-series or a geometric series. Now, how do we choose our p-series or our geometric series? Usually we have some kind of fraction, and it's nice to consider the dominant force behind the numerator and the dominant force behind the denominator, so kind of the largest piece. Constants don't grow. Logarithms do. So for large values of n, logarithms dominate constants, polynomials dominate logarithms, and exponentials dominate polynomials. And then remember, after you've chosen a series, you have to show that it works. So you either need to demonstrate that the inequality goes in the correct direction for the direct comparison test, or that the limit of the ratio of terms is a finite number for the limit comparison test. So let's think about what we might want to compare this series to. On the bottom I have a polynomial. It's a quadratic term and a constant term. So I guess the quadratic term is going to dominate. That's going to really define the character of the denominator. The numerator, I have 3n. This simpler series is just a harmonic series times 3. It is easy to deal with because I automatically know it diverges. Now I need to decide if I'm using the direct comparison or the limit comparison, and I need to make sure that this comparison is actually valid. For doing this, sometimes it's easier to think of your comparison series in its unsimplified form. The left terms have a larger denominator, so they are smaller overall. This is not the correct direction for the direct comparison test. So at this point in time, I would like these series to do the same thing, both diverge, but I don't know that they do the same thing. I don't know that this is a good comparison. Let's use the limit comparison test. I'm going to take one of these series and put its terms on the top. And I'm going to take the other series and put its terms on the bottom. To simplify, I flip the bottom and multiply. Cancel off the 3's. Now from this step, you could say that this is a rational function, a polynomial over a polynomial. The top and the bottom have the same degree, so its limit is going to be the ratio of leading coefficients. Or you could do one more simplification step, come here to the right, and see that 1 over n squared goes to 0, so this limit is 1. In either case, my limit is positive and finite. So by the limit comparison test, in particular, our series diverges because our comparison series diverges. Here's another series, and we want to decide whether it converges or diverges. The divergence test doesn't help us, the ratio test doesn't help us, and the integral test would be quite messy. So choose a series to compare, and then pause the video and prove that your comparison is valid. The top and the bottom are polynomials, so I'm going to pick off the highest term in the top and the bottom, and I'm going to hope that that is the term that really dominates the character of these polynomials. So I'm going to compare this to n squared over n to the 5th, which is the same as 1 over n cubed. That's a p-series, so I know what happens to it. It converges because p is equal to 3, and 3 is bigger than 1. For the direct comparison test, I would have to decide which of these series have bigger terms for large values of n. So let's go through this process of deleting things. If I make the numerator smaller, that makes smaller numbers. If I make the denominator bigger, that also makes smaller numbers. So my inequality goes the wrong way to use the direct comparison test. You don't always have to check whether direct comparison will work. Sometimes it's actually kind of tough to figure out which is bigger and which is smaller, and if you don't want to figure out which is bigger or which is smaller, you can just jump to the limit comparison test. So let's evaluate the limit, as n goes to infinity, of the ratio of my terms. My mystery series has this rational function as its nth term. My comparison series has 1 over n cubed as its nth term. Flip the n cubed and multiply. And again I see I have a rational function, a polynomial over polynomial. They have the same degree. Both the numerator and the denominator have degree 5. So this limit is going to be the ratio of their leading coefficients. N to the 5th is multiplied by 1 on the top and 1 on the bottom. So this limit is 1. 1 is positive and finite. So that is the limit comparison test telling us that this is a valid comparison, that these two series do indeed behave the same way. Now, something not to forget when you're doing these is it's not enough to come up with a comparison, because maybe your comparison is not good. Maybe you compare it to a series that does something different. You have to prove your comparison is good, either by showing that the inequality goes in the right way, in this case it doesn't, or that your limit from the limit comparison test is a positive finite number. We want to know whether this series converges or diverges. Take a second, pause the video, see if you can give a completely justified answer to that question. There's a little bit of fine print to this one. We do want to use the comparison test. I certainly wouldn't want to have to integrate this. It fails the divergence test. The divergence test doesn't tell us one way or another. The ratio test also not very useful. In order to use the comparison test, I need all of my terms to be positive. And sine is not always positive, but 2 plus sine, the smallest it could ever be is when sine is -1. So indeed, these are positive terms. And that's nice because it means we're in the running for using one of our two comparison tests. So let's figure out what we should compare this to. Again, I'm going to try and ignore the small terms. 2 plus sine k is between 1 and 3, so I'm just going to ignore it. So this simplifies to 1 over k times the square root of 2 minus 1. So this is a p-series. P is the square root of 2 minus 1. The square root of 2 is about 1.4. So at least the square root of 2 is certainly less than 2. This p is less than 1. So our comparison series diverges. Let's see whether our inequality goes in the right direction to use the direct comparison test. We already saw that 2 plus the sine of k is bigger than or equal to 1. So that means k times 2 plus the sine of k is bigger than or equal to k. K is a positive number. I multiply both sides of the inequality by it. Now I divide both sides of the inequality by k to the root 2. That's also a positive number, so it's not going to flip the inequality. So my comparison series diverges. I think of its terms as being so big that when I add them together, the stack goes to infinity. My original series has terms that are even bigger. So for these even bigger terms, certainly their stack goes to infinity as well. This is the correct direction to use the direct comparison test. So by the direct comparison test, our mystery series diverges as well. Here's a really similar example to the example we just did. This is a good opportunity to check that you understood the last explanation. So pause the video and see if you can write out a complete justification as to whether this series converges or diverges. Just like last time, we want to make sure that we're even in the right neighborhood to use the comparison test. Comparison test only works when our series have positive terms. So let's make a little note up here. M starts at 1, so the smallest 3m can ever be is 3. The smallest sine of anything can ever be is -1. So indeed, we are adding up positive terms. The divergence test doesn't tell us anything helpful. The integral test would be quite difficult. The ratio test also would be inconclusive. So the only tests we have left in our toolbox are our two comparison tests. Let's think about a series to compare this to. If I'm just going to ignore this term, this is the smallest term, 3m is going to infinity, sine root m is going between 1 and -1. This series would look like 3m over m squared, which is 3 times the harmonic series, which diverges. However, my inequality doesn't go in the right way to use the direct comparison test with these two series. The inequality isn't even consistent. Sometimes sine m is positive and the left one is bigger. Sometimes sine m is negative and the right one is bigger. So there's not even a consistent inequality. Ordinarily, at this point, I would go to the limit comparison test. But in this case, I'm going to hang on a little bit longer. So first off, my hunch is that this series diverges. I don't know for sure yet that my comparison series actually does the same thing that my mystery series does, but it's a hunch. I have a hunch that this series is divergent, so what I need is a comparison series that's smaller. I need a series whose terms are definitely big enough to add up to infinity, but whose terms are also less than my mystery series, because then my mystery terms will also be big enough to add up to infinity. That series isn't 3 over m squared, but it might be similar. So I know that the smallest this can be is 3m minus 1 over m squared. This is still not a super easy sequence, because if I want to know whether its series converges or diverges, it's still not clear. But I'm going to write this as 2m plus m minus 1 over m squared. Because that, when m is large, is bigger than 2m over m squared, which is 2 over m. These terms make up another series whose convergence or divergence is easy to ascertain, but in this case the inequality will go in the right direction. So I'm going to let my bn terms be 2 over m. When I add up my bn's, I get twice the harmonic series, so the series diverges. And now my inequality goes the right way. My mystery terms are, as we just saw, bigger than my comparison terms. So, by the direct comparison test, comparing to twice the harmonic series, our mystery series diverges. If you're writing this down and you need to justify your work, after you choose your comparison, you need to state whether it diverges or converges. And then you also have to make sure that the inequality goes in the correct direction. This is why our original comparison series, 3 times the harmonic series, did not work. Now let's say we wanted to stick to our original comparison series and use the limit comparison test. Let's see how that would work. I know that our comparison series diverges because it's 3 times a harmonic series. So I need to evaluate the limit of the ratio of the terms. My mystery terms are 3m plus sine root m over m squared, and my comparison terms are 3 over m. To simplify this, I'm going to flip the bottom and multiply. Simplify a little bit. Now from here, I need to do a surprising amount of work to figure out this limit. Remember, our limit laws only apply when limits exist. If this limit, say, were 1, then I could just replace this with a 1. But this limit does not exist. So the only tool I have to deal with this is the squeeze theorem. Sine root m, sine of anything, is never bigger than 1 and never smaller than -1. So I can bound this problem part of my limit by the sequence -1 over 3m and the sequence 1 over 3m. And they have the same limit as m goes to infinity. So, by the squeeze theorem, the limit as m goes to infinity of sine root m over 3m is equal to 0. Bringing that back to our original computation, that tells me this limit is 1. Now again, if you had to fully justify your work, you would need to go through the squeeze theorem to show that you had, in a rigorous way, evaluated this limit. Now I've shown that my comparison is valid because this limit is positive and finite. So, by the limit comparison test, our mystery series diverges because we chose a series to compare it to that diverged, and we proved that that comparison was valid. Let's do another example of finding out whether a series converges or diverges. Exponentials grow faster than polynomials, so that tells me the divergence test is inconclusive. The terms I'm adding up are indeed getting closer and closer to 0. The divergence test doesn't help. I wouldn't very much like to integrate this, so the integral test is also out. The ratio test could work, but that log n is going to make things complicated, so let's think about a comparison test. I want to find a series to compare this to. The numerator only has one part to it, the denominator has two parts, and logarithms grow very slowly. They grow much more slowly than exponential functions, so I'm going to guess that a good comparison series would be what I get if I just ignore this smaller bit, this logarithm. So I've chosen a comparison series, but the comparison test is no good if I don't know what happens to my comparison series. And this one is not immediately clear. It's neither geometric nor a piece series, but this would be easier to apply the ratio test to than my original series. So I'm going to do a two-step approach here. I'm going to do a comparison test, and on my comparison series, I'm going to do ratio test to figure out whether it converges or diverges. This comparison series is a great candidate for the ratio test. Its terms are positive, so I don't have to worry about absolute values. I'm going to compute the ratio of consecutive terms and take the limit as the index goes to infinity. For my n plus first term, n squared becomes n plus 1 squared, 2 to the n becomes 2 to the n plus 1, and my denominator is n squared divided by 2 to the n. Now I flip the denominator and multiply. As usual, I've grouped terms that look similar. Now I can see that for my first bit here, I have a square over a square. So the limit is going to be the ratio of their coefficients, which is 1. On the right, if I divide the top and the bottom by 2 to the power n, I get a half. This limit is a half. That's how we defined r. And r is positive and less than 1. So our comparison series converges by the ratio test. So now I have my comparison series ready to go, but I haven't shown that the comparison will actually work. I haven't shown that actually these two series behave similarly. Let's think about which series has larger terms. The series on the left has a larger denominator, so it's smaller overall. This is the correct direction of an inequality to use the direct comparison test. The fact that my comparison series converges means its terms are small, and these terms are even smaller. So that means my mystery series converges as well by the direct comparison test. Again, remember what we need to show for the direct comparison test. We need to show whether this converges or diverges. In this case, it was a little harder than normal. And then we also need to show that the inequality goes in the correct direction.